go further. Okay, so, this is kind of where we're actually getting into confidence interval. And then from here, we'll build up and get into hypotheses testing. If any of you have already looked through the chapter on the handouts, then, you will, of course, kind of see that this is where chapters 9 and 10 take us. So for these ones, instead of actually doing an activity like we normally do, I thought I would actually walk you through some of the bigger, longer problems, because these ones, can get a little challenging in terms of just how do they want it answered, what the process is and stuff. And the other thing that I have done for these examples is actually I have created these sort of templates that I call them. So let me go ahead and share these with you. Now, you guys will not be able to make changes to this document because you are only assigned a viewer permission on these, but you will be able to make a copy or download these, and you can use these to work through examples. So these are some of the examples that we'll be talking about. So this is from chapter 9. And let me share the link with you from chapter 10 also. And again, guys, just make sure you're in your ames.edu email address, so that way you will be able to access these files. So the first link will take you to the chapter 9 document, and then the second link will take you to the chapter 10 document. And actually, I'm gonna go ahead and clear these answers out because I think this is the last time when I used. All right, so the first example we're looking at is this one over here. This is example number 9 from your homework. So you can see this one is a problem number 9.1.27. So, the 27th problem from the textbook. And you will see on the bottom of your Google Sheets, I have given you those numbers. So 9.1.27, 9.1.41, and then from the 9.2 section. So that's kind of how you can relate those. So this example, the first one that we're looking at over here, as you can see, is talking about, and I'll make this guy a little bit bigger so you can see it better. So this one is saying a random sample of 1,016 adults in a certain large country was asked, do you pretty much think televisions are a necessity or a luxury you could do without? So out of these 1,016 adults surveyed, 524 indicated that televisions are a luxury they could do without. So that's your basis over here. And you can see they've given you links for the standard normal distribution table. And, of course, you guys worked on standard normal distribution tables and the normal distribution in the last chapter. So, obviously we're building up on that with these confidence intervals. So the first question they're asking you is actually just to come up with a point estimate for the population of adults, who think that televisions is a luxury they can do without. So, they're basically saying they don't need television, they're going to be okay without it. So they're telling us that there were a total of 1,016 adults who were surveyed. So that's, of course, your random sample size, right? So that's going to be your N value. So that's the 1,016 you're going to plug in here in the N value. Now, the X in this case actually represents this little information here, where they're telling us that, out of the 1,016, 524 said, this is a luxury that they can live without. So the 1,016 is the N value, and then the 524 is going to be your X value. So that's what we're going to plug in over here. So 524, yeah. So 524. And you can see the way I have created these documents is I'm giving you the formula over here. So you will kind of know when we talk about the point estimate That's the variable p hat, that little tilde on the top is what we call as p hat. And you're literally just doing 524 divided by 1016. So you can type in the numbers, or what I do, again, you've seen me do this normally, is I just click on the cell number. And so that way, when you guys use this file for your own homework, all you literally have to do is go ahead and erase these two numbers and type in what you see in your example, and it will automatically calculate. So you can see if instead of 524, we change that to, let's say, 624, you will see it automatically will calculate the p hat. So, that's why you kind of can use the cells instead of typing the numbers in. So this is our p hat value, the point estimate, and we're getting 0.5157. And then you can see what your rounding instructions are. And based on that, you can type in your answer. So this one is saying 3 decimal places. So since you have 0.5157, of course, round it to 3 decimal places. And what will that rounded answer look like over here, guys? When you go from 0.5157 to 3 decimal places?
0.516.
Yeah, so regular rounding rules. So this will become 0.516. Check your answer. So now this is where, we have to kind of check and see if we can do a confidence interval or not. So you can see this guy is saying verify that the requirements for constructing a confidence interval about P are satisfied. So this is where, this is kind of where that checking comes into place. So the first thing we have to see is, when we multiply n times p hat times 1 minus p hat, is that number going to be greater than 10? And that's what we're doing over here in this little box over here. So we're going to check and see if our answer comes out to be at least 10 or more than 10. And then the other one says your random sample, so this small n represents our random sample of 1016. Is it at least less than or equal to 5% of the entire population? So the capital N, will represent the entire population of this country that they're talking about. So honestly, in the example, they're not telling us what the population of the country is. For that matter, they're not even telling us which country we're looking at. All they say is that it is a certain large country. So in this case, for that 5% population requirement, we're actually just going to assume that we meet that requirement. So you will see in this box over here, I'm telling you, assume that the sample size is less than or equal to 5% of the population size. Normally, the problem does not tell us what the population size is. So we will make the assumption that our sample size is, less than or at least 5% of the entire country's population. But let's go ahead and calculate this n times p hat and 1 minus p hat. So again, I'm going to use built-in functions for that. So our n value, again, I'm going to click on that cell, multiply that by our p hat. So again, click on that cell for p hat, multiply again. And then this is where in parentheses, I'll type in the 1 minus p hat. And, of course, for the p hat, I'll click on that cell again. So you can see, once you change those x and n values, this calculation will also automatically change. And you will see, guys, in this case, we are pretty large number, obviously the requirement was at least 10, but we're definitely more than 10. So those two requirements are being met. So when you start looking at this, we will say the sample size is stated, the sample is stated to be a random sample because, obviously they're telling us this is a random sample. So it's stated instead of assuming, right? Because they're telling us this is a random sample. So that's the option there. Then we will say the value of, and this is where we did this calculation, the n times p hat 1 minus p hat. So this value was, and again, they want us to do 3 decimal places. I think that guy was 253 something. So 253 and then 3 decimal places will be 748. okay, which is obviously greater than equal to, because remember the minimum requirement was 10, but obviously this is greater than 10. Now here is where we will say that the sample size can be assumed, because again, they're not telling us if this is, 5% or less than 5% of the population. So this one here is where we are assuming it is going to be less than or 5%, of the population size of this country. So this is where you're verifying that we meet the requirements to be able to do a confidence interval for this example. So again, check your answer. And now this is where you will see they're having us actually constructing the confidence interval. And then guys, remember, with confidence intervals, they tell you what degree they want. So normally the usual ones are, of course, 90%, 95%, as you see here. And is it 98%? I believe so. So those are the three common ones. But, obviously, they can change that to, they can do 85%, they can do 97%, they can do 99%, but usually, you will see a lot of 90 and 95% in there. But confidence interval can be at any degree. It just depends on, what they're looking for. So here they're saying construct and interpret a 95% confidence interval for the population proportion of adults in the country who believe that television is a luxury they can do without. So when we're talking about confidence interval, the idea is, guys, if we kept doing this experiment, right, out of these 1,016 people, we asked them, can you do without a television? And we kept repeating this experiment. So we kept selecting new people for that 1,016 random sample, because, it's a large country. We can keep moving areas, we can keep changing demographics or whatever, and we can keep collecting this random sample of 1,016, and each one of them is going to give you a little bit of a different answer, right? Not always we're going to get 524 people who say, yeah, it's we can live without TV. So the idea is, if we were to take the results of this survey and expand it to the entire country, well, can we say, because we're getting that point estimate of 0.516, so that's approximately 51.6%. So the idea is, with what confidence can we say that this result is going to be true for the entire country and not just for this sample, right? So that's where this idea of confidence interval comes into play. So with the confidence interval, you have, we can say, we're basically confident or 95% confident that, our result will stay near 0.516, and then you can kind of do a plus or minus, because you can go below or above. So that's where this idea of the confidence interval comes into play. So for the confidence interval, this is actually that big formula, if you look under your textbook, that they will have you working on. And so based on that, you can see we're using the p hat. The z alpha sub 2 is actually going to be our z value, from the normal distribution. And then again, you will see inside the square root, you have the p hat, 1 minus p hat, and n. So all of those values have been calculated with the exception of the z alpha sub 2. So that's kind of part of our calculation over here at the bottom. So your alpha, of course, is going to be, if you're doing 95% confidence interval, your alpha is actually going to be 1 minus this 95%. So basically you will do 1 minus 0.95, which of course will come out to be 5%. Oh, instead of minus, I put a decimal there. There we go. So alpha is basically, if you're doing a 95% confidence interval, is the remaining percentage. If you did 97% confidence interval, alpha would be 3%. So it's whatever is the other half when you do 1 minus that number. Obviously, as you can imagine, alpha divided by 2 is going to be that 5% divided by 2, or 0.05 divided by 2. So 0.025. And again, you will see I'm working with, if I can click on the cells, then I'm working with the cells to do the calculation, because anytime anything changes, we can go ahead and come up with that. So now that we know that our alpha divided by 2 is 0.025. We can actually go into our normal distribution table. Let's see, 0.025. Actually, I think I need to be on the other side of this table, table 1. I'm trying to make this bigger so I can kind of show you. So what you are doing is once you find that alpha divided by 2 value of 0.025, we have to figure out, because you know that's your percentage, that's your probability. Now you have to figure out what the z value for that is going to be. So in the body, we actually need to find 0.025, and I can see the 0.02s over here. And there we go, 0.025, 0. So this is the percentage we're looking for, and that corresponds to negative 1.9 over here and 0.06 over here. So you're actually getting negative 1.96. But in this case, we're actually looking at this more as a critical value and less as a z-score. So we actually don't have to worry about that negative sign. We're just interested in the 1.96 number and not really with the negative sign. So that's kind of how you are using this standard normal distribution table. So you're finding the percentage that you get from the alpha divided by 2, and then based on that, you have to find your z-score. So 1.96 is the z-score that it comes out to be. And that's what we're going to put here, 1.96. And then once you have calculated your z value, then literally you're just plugging in into this formula over here. So again, I'll show you how to do this with the built-in cells instead of typing the numbers in. So for the lower bound, so that's going to be the one with the minus sign here. The upper bound is going to be the one with the plus sign. So equal to, you can see here we have p hat first. So p hat was this cell minus, then we're doing the z alpha sub 2, which is this number of 1.96. And then we're going to multiply that with the square root function. So sqrt, open parentheses. Then again, we are doing p hat. So go back to the top, times, and then you're doing 1 minus p hat. So again, in parentheses, we'll do 1 minus, click on that p hat cell again, close parentheses. So this is just the numerator, guys. We did p hat times 1 minus p hat, and then you're dividing by n, and the n value is going to be the 1016. So click on that cell. And now you will see when I close parentheses, this close parentheses is actually for the entire square root function. So in parentheses, we're putting that entire square root. And then, of course, by default, Excel, Google Sheets, they use order of operations. So they'll do the calculation themselves. So this gives you your lower bound. And you can see our lower bound is coming out to be about 48.5%. So just slightly lower than our point estimate here. For the upper bound, you will see the formula is exactly the same. The only difference is we have p hat plus the z times the square root. So what I'm going to do is copy the formula that I put in the lower bound, and I'm just going to paste it here for the upper bound. And then right at that beginning, just change that minus sign to a plus sign. And you don't have to retype the formula in, and you will see that helps us calculate our upper bound. So for our 95% confidence interval, we're basically saying that we are going to be anywhere from 48.5% to 54 point, if we round it to 3 decimal places, 1 decimal place, 54.7%. So we will say, okay, we have a 95% confidence that 48.5 to 54.7% of the population will say, TV is a luxury that they can live without. So that's kind of how this thing is working out to be. So let's go ahead and close this guy. Now here, guys, you are choosing Is it going to be part A or is it going to be part B? Is there a 95% probability or is there a 95% confident that the population believes television is a luxury? So which option is it going to be, A or B?
Is it B in this case?
Yeah, Cody, very nice. It is going to be B, right? Because we are calculating the confidence interval here, not the probability. So, they're trying to throw you off. So remember, this is a 95% confidence interval. So you are going with option B. So we are 95% confident. And then this is where you are putting in your numbers. And again, guys, we are rounding this to 3 decimal places. They tell you that right over here. And leave it as decimals, not as percentage. So we had, let's see, for that lower bound, we had 0.485. And then for the upper bound was 0. Let's see, 547. And that's going to be our 95% confidence interval. So remember, this was about how many of these adults believe that television is a luxury they can do without. So now they are saying, is it possible that the supermajority, that would be more than 60% of adults in the country, believe that the television is a luxury they can do without? Is this likely? So looking at our confidence interval, can we say that the supermajority, which is more than 60% of the adults in the country, believe that television is a luxury they can do without? So is it likely, not possible, possible, but not likely? So where are you guys leaning with this choice over here, looking at the confidence interval?
I'd probably go with the third option.
The possible but not likely. Okay. So we are saying it is possible but not likely that supermajority of the adults believe television is a luxury they can do without, because in your 95% confidence interval, it does not contain, and remember, we're looking for 60%. So if you're looking for 60%, that's 0.6. And you can see our interval goes from about 48% to 54, maybe even 55% if you round it up, but you don't have the 60% in there. So that's what you have to say, is that it's possible but not likely, because your confidence interval does not contain that 60% value in there, and they're asking you to type an integer or a decimal. So we'll actually leave it, I believe, as 0.6 in the decimal format. Yeah. Now, the last part here is actually asking you use the results from part C. So that's going to be these answers here to construct a 95% confidence interval, but this time the confidence interval for the population proportion of adults in the country who believe that televisions are a necessity. So remember, up until this point, we were doing this for people who believe that televisions are a luxury they can do without. But now we're saying this is for people who believe that television is a necessity. So how will we calculate these upper bounds and lower bounds based on answers from part C, which was a 95% confidence interval for the other group of people? And obviously you will see I've given you the space over here to do that. So we know what the confidence interval for people who can do without is, but now this is about people who think it's necessity. So you can see you're basically doing 1 minus the lower bound here. And then for the other one, we will be doing 1 minus the upper bound. And that will actually give you the confidence interval for the people who say, television is a necessity. Now, obviously keep in mind the smaller number will be the lower bound and the larger number will be the upper bound. So for the lower bound, the smaller number is 0.4535. What did I do? There we go. 4535 will of course become 0.454. And then for the other one, the larger number will be the upper bound. So that's going to be 0.515. So literally in this case, you don't have to go back and redo any of the calculations. Now that you have the confidence interval for the other group, you know, just subtracting those numbers from 1 will give you the confidence interval for, you know, this group. So questions on this example over here, guys. How to calculate your confidence interval. Okay. So, you know, since these problems take a little bit of a longer time, let's do one from 9.2. Let me just make sure. Save this guy. Okay. There's another very small example over here from 9.1. Just to help you kind of calculate the margin of error, or I think it works backwards to calculate the sample size. I will try and see if I can post a video for this, but I wanted to get into, like I said, 9.2. So let's pick, I didn't realize I hadn't cleared these numbers out. Okay, so this one is talking about test statistic. There we go, 9.2. Okay, and this one is problem number 12. Yeah, 9.2.31. Okay, so this one, again, you can see on the right-hand side, they're giving you the data values, but this one is basically saying the following data represent the pH of rain from a random sample of 12 different rain dates. The normal probability plot suggests the data could come from a population that is normally distributed. So again, you will see we're still continuing with normal distribution here. A box plot indicates that there are no outliers, and they're asking us to complete parts A through D. And this one, and I kind of love this table because again, you know, this is based on t-distribution. We'll talk about this again, kind of like we did with the normal distribution. We'll use this in our calculation also, but let's start with our data here. So I'm actually just going to hit copy to clipboard. If you guys are working in Excel, you know, of course you can open this in Excel. So copy to clipboard. And then I'm going to bring this over here where I have data from homework. Okay, I guess I have to hit Control C. I didn't realize that. There we go. So we've got our data set over here, and I will actually come back to that one. So you can see in the first part of the problem, they are actually again asking us to calculate the point estimate rounded to 2 decimal places. So again, I've given you how we can calculate that over here. So you've got your formula for this. So basically just use the built-in function for mean, or you can use the formula over here. So if you just want to use the built-in function, remember that is the average function in Google. So average, and then you're taking the average of these data sets from our, you know, rain pH levels. So you've got your 5.015. They wanted to round it to 2 decimal places, so 5.02, right? Check that. So that's your point estimate. But remember now, just comparing it from what we did in 9.1 to 9.2, 9.1 was just taking the X divided by N, right? Because you had a random sample, and then out of that survey, how many people said television was a luxury. Here, they're actually giving you the raw data, right? So the calculation is a little bit different from what you did in 9.1. Okay, now you can see they're talking about constructing that 95% confidence interval for the mean pH level of the rainwater. And again, you can see your different options over here. If repeated samples are taken, 95% of them will have a pH of this and this, 95% confidence that the population mean of pH is so-and-so, or 95% probability. So same thing, you are talking about a 95% confidence interval. So you are looking at this second option over here. So let's talk about how to calculate this. So first we have to calculate our degrees of freedom, because we need that to calculate this t-value over here, so you can see that we have basically 12 random samples, because they're telling us these are coming from 12 rain dates. So your n value is going to be 12. Your degrees of freedom is basically n minus 1. So we end up doing n minus 1. So obviously that's going to be 12 minus 1, which it comes out to be 11. Now, the next thing you can see that we need for this confidence interval, and if you look at this formula here, we need the X bar. So we've already calculated the mean. We need to calculate standard deviation. We'll need square root of n. Of course, we know n is 12. And then we'll need the t-value. So the first thing we can do is the square root, the standard deviation, the S value. So again, you can use this formula, which is again from your textbook, or use the built-in function. Now remember guys, this is a sample. So since this is a sample, you are going to use the standard deviation dot S formula for the sample. So again, standard deviation dot S, and then go back to your original data and calculate the standard deviation for it. And you can see your standard deviation comes out to be 0.407174, keeps going. So let's work on the t-value next. So again, this is a 95% confidence interval. So just like we did before, alpha will be 1 minus the 0.95. Obviously, alpha divided by 2 will be 0.025. So that part actually is the same from what we did in the previous example. Now for your t-value is where we go to this little critical value table here. And this time, the way this table is going to work is that you're actually going to take degrees of freedom with that alpha divided by 2 value that we just looked at. Come on, buddy. So degrees of freedom, remember, was n minus 1, so that was 11. Our alpha divided by 2 came out to be 0.025, which is right over here. So based on that, we have to come up with our t-value, and that looks like it's going to come out to be this number right over here. So that guy, it's hard to see, is coming out to be 2.201. So again, alpha divided by 2 on the top, degrees of freedom here on the left, and then where those two values meet is going to give you your t-value. So 2.201, let's close this. 2.201. And now we can go ahead and clear this out. All righty, so you can see we've got everything we need to be able to calculate our lower bound and upper bound. So again, I'm just going to type in our formula here. So you can see the first part says X bar, that's our mean, minus t-value, so that's going to be the 2.201, multiplied by S, which is your standard deviation. So we just calculated that over here, divided by square root of n. So again, our square root function, SQRT, square root of n. And remember, your n is the 12. So not the degrees of freedom, the actual 12, your random sample. And that is going to be our lower bound. And again, the only difference between lower bound and upper bound is going to be that minus sign needs to be changed to a plus sign. So change that to a plus, and that will give us our upper bound. So using this, back to our problem, and they are asking us to round this to 2 decimal places. So 2 decimal places will be, let's see, for the lower bound, we have 4.756, which will become 4.76. And remember, this is the mean. We are talking about the mean pH value. So this is not, going to be decimal answers, because your mean is coming out to be 5.02. So, what is that 95% confidence that your mean can be anywhere between 4.76 to, what will this guy come out to be, 5.27? Okay, so all they're doing here now is they're changing it from 95% confidence interval to a 99%. So, when you go from a higher degree of confidence interval, what do you think will happen to these lower bounds and upper bounds? Are those numbers going to get closer to that mean of 5.02, or are they going to go farther away? So when you increase that confidence interval, Cody?
I was going to say farther away.
Yeah, so the more higher degree you look for in that confidence interval, guys, your margin of error actually gets longer, it gets bigger. So if we did 90%, the numbers would actually get closer to your mean. So that's kind of how that confidence interval works out. So as you can see, we have most of this calculated. All we really have to do is change the t-value, since we're changing the confidence interval. So as you can imagine, your alpha will now be 1 minus 0.99, which of course then means alpha divided by 2 is going to be even smaller, 0.005. So we'll need to go back to our critical value table over here. Okay, so again, our degree of freedom is 11. Alpha divided by 2 is 0.005. So let's see, these guys are meeting at 3.106. Okay, so let's put that here, 3.106. Clear this out. And again, what I'm going to do is, because everything else will stay the same, the only thing that's going to change is the cell for the t-value. So I'm actually going to go ahead and copy my formula from the 95% confidence interval. So as you can see, our n value is not going to change. The s value is not going to change. The only thing that's going to change is where your t-value is going to be. So I'm going to change that cell of B20 to E20, where we have the new t-value. And then of course, you can see our mean, the F2 cell obviously also does not change. So just change the box for the t-value. For the upper bound, I've already copied my formula over, so I'm going to change that minus sign to a plus sign. And we have our upper bound and lower bound for the new confidence interval. So again, rounding this to 2 decimal places, this is again a 99% confidence. We are looking at lower bound of 4.64, so that will become 4.65. Upper bound will become, let's see, it will stay at 5.38. Okay, so like Cody said, our confidence interval actually became bigger. The numbers spread out a little more when we went to a 99% confidence interval. So that's what they're asking you to do here in part B, is they are saying, What happens to the interval as the level of confidence is changed? Explain why this is a logical result. So as the level of confidence increases, the width of the interval, so where do we go here, guys? Increases or decreases?
Increases.
Increases, yeah, because you are further out than what we were. And then they're saying this makes sense since the point estimate, sample size, margin of error decreases or increases as well. So what again would you choose here? Did our point estimate change? Did our sample size change, or did our margin of error change?
Margin of error.
Yeah,
Okay.
sample size is still 12. Point estimate is the mean. None of those numbers change. The only thing that changes is margin of error. And of course, your margin of error is also increasing because your width of the interval increased based on the margin of error. So that's kind of how the margin of error and confidence intervals are connected together. So any questions on this example over here? So just to show you how we work with the Z value, which was our standard normal distribution table, and then how we use that with the T distribution table. So that's kind of the difference between 9.1, 9.2. Now, I wanted to show you an example from chapter 10. Let's see. And again, just to let you know, there is another example here, 9.243, which again kind of deals with sample size, the different confidence intervals over here. So I will again try and see. I may have a video recording on this one. I will try and see if I can post that for you guys. Let's go into 10.1. 9.3, just to let you know, is basically where they put everything together and then they have you decide, do you use a standard distribution table or do you use the T distribution table? So that's kind of where 9.3 comes in. So this is where we're actually getting into hypotheses testing over here, guys. So let's maybe try and do, let's do number 9. So this one here, oh, sorry, didn't mean to do that. So this one is saying the standard deviation in the pressure required to open a certain valve is known to be, 0.9 PSI, and that's of course your sigma symbol. They're saying due to changes in the manufacturing process, the quality control manager feels that the pressure variability has increased. So, in this case, we're again basically doing a comparison. So we're saying the standard deviation in the pressure that is required to open a valve is, 0.9. But now they are saying with some changes that happen in the manufacturing process, the quality control manager is saying that the pressure variability has increased. So he is saying that, that standard deviation has changed from 0.9 PSI. And that's what we're basing our hypotheses testing on. So for this, remember I shared the second link with you where you have these, oh, hold on a second. Did I pick the wrong example? I think I did. Because I have 10 to 21. Are they the same example? I'm sorry, guys, I confused myself over here. No, I think I have the right example. I just have the wrong number. I'll change that number on the handout. Okay, so let's talk about the hypotheses over here. So they are telling us that our sigma value is 1.3 PSI. Actually, I think I did not create a document for this. That does not look what I want. Okay, so our sigma value is 0.9 PSI. Now they're asking us to start out by stating the hypotheses for the null and alternative. So remember the H sub 0 represents the null hypotheses and H sub 1 represents the alternate. Some textbooks will use 0 and sub A for those, but our textbook goes with 0 and 1. So in this case, we are basically saying, okay, so the null hypothesis is where we are saying the PSI is equal to 0.9 because that's what they're giving us. The quality control manager is saying that he thinks that the pressure has increased, right? So again, we are going with sigma, but he is saying it has increased. And they're telling us that right over here, that it has increased. So greater than, and we will say 0.9. There we go. Now, if, guys, again, just different examples, if they give you that the pressure has reduced or decreased, then, of course, you'll use the less than symbol. So, look at the wording of your example to see which symbol you need to use. If they say change, so instead of saying it has increased or it has decreased, if they say change, then that's when you use the not equal to symbol because they're not specifically saying if it's gone up or gone down. They're just saying it's different from what it was originally. So that's when you do the not equal to symbol. Okay, so now this one is just saying which of the following type is a type 1 error. And again, if you have not read your textbook yet, definitely go and look through some of these descriptions. So when we talk about type 1 error, we're saying type 1 error is committed when the null hypothesis is rejected when actually it is true. So the null hypothesis is, our standard deviation equals 0.9 PSI. So in this case, based on the fact that null hypothesis is rejected when it is actually true, is when type 1 error occurs. Which option will you go with over here? The manager rejects. So you've got two options with the manager is rejecting or the manager fails to reject. Remember, type 1 error happens when null hypothesis is rejected when in fact it is true. So did the manager fail to reject or did the manager actually reject the null hypothesis?
Fails to reject.
Fails to reject, okay. So you are going with either options B and D where they're saying fails to reject. So we are saying the manager fails to reject the hypothesis that the pressure variability is 0.9 when in fact pressure variability is greater or when pressure variability is true. So in this case, of course, we are saying null hypothesis is rejected when it is true. So this one would make sense. And let's see if this comes out to be true or not. I'm actually going to erase some of these lines over here. Okay, so you can see they said that is actually incorrect. So in this case, Cody, and of course for the rest of you, it is actually going to be the manager is rejecting because he didn't fail to reject. He is actually himself saying that he thinks there is a change in variability because he is saying there is an increase in the variation of the variability. So he is actually rejecting the null hypotheses. I hate when this guy does that. Okay, so he actually rejects the hypotheses when it is true pressure variability. Okay, let's check that. So, again, it just really comes down to the wording in English, and you just kind of have to be careful about, how the sentence is written out. Now we're talking about type 2 error. And again, just to remind you guys, type 2 error is committed when the null hypothesis is not rejected, when actually the alternative hypothesis is true. So type 2 error happens when null hypothesis is not rejected, when the alternative hypothesis is true. So again, I'll give you guys a second to look through the options. Let's make this just a little bit smaller. So A, B, C, or D, the manager fails to reject the hypothesis that the pressure variability is 0.9 when it is the true pressure variability. The manager rejects the hypothesis when the true pressure is greater than 0.9. The manager fails to reject the pressure variability when true pressure is greater than 0.9, and the manager rejects the hypotheses when the true pressure is variable. So remember, type 2 happens when you do not reject null hypotheses, when alternate hypothesis is true. So which one seems to kind of go along those lines, that we're saying you should have rejected null when you didn't because the alternate was true? And remember, the alternate says the pressure variability is greater than 0.9.
Would it be C?
Okay, so you're going with C. The manager fails to reject, which is good because we are saying you do not reject the original hypotheses when the true pressure is greater than 0.9. All right, wonderful. That option definitely looks good. And there you go. All righty, very nice. So this one was more based on, kind of the theory behind your null hypotheses, alternate hypotheses, and how to kind of understand and interpret, what the type 1 error, type 2 error kind of makes sense in this case. So did any of you have a question on this one over here? Okay, if you guys don't mind, I would like to show you an example from 10.2, and I just realized where the confusion happened was the Google Sheets that I was looking at was actually from 10.2, and I was thinking that's 10.1. So I would like to show you an example from 10.2, and like I said, I just realized these are 10.2 problems and not from 10.1. But if you guys have to leave, if you have another commitment you need to go to, you are definitely welcome to leave. I know we're right at that end of the class time, so I don't want to, keep you here any longer. But if you can't stay, then I would like to show you an example from 10.2, just to at least kind of give you guys an idea of how to work through, some of these examples over here. And, it will not count against your attendance if you have to leave, because obviously you're here for the entire class period. But again, just I wanted to let you know that if you have something and you have to leave, you can leave, and I will still have this recording, so you can always come back and watch the recording for the 10.2 homework problem, okay? All right, guys, so the example here, this is the 10 to 21. And this is the worksheet for it. So let's go ahead and clear this out. Alrighty, so this one here. Okay, let's take a look here. So this one is talking about 20 years ago, 49% of parents of children in high school felt that it was a serious problem that high school students were not being taught enough math and science. So this was 20 years ago, okay? And 49% felt that students were not being taught enough math and science. Now, we are saying a recent survey found that 281 of 900 parents of children in high school felt that it's a serious problem, students are not being taught enough math or science. So they are basically asking us, do parents feel differently over this 20 period time? So you've got 49% from previous result, 281 out of the 900 now present, right? So they're saying use alpha as 0.05 as your level of significance. So the first thing we're actually going to do is go ahead and calculate what the parents are thinking about right now, what's going on with the parents right now. So let's take a look at how these calculations are working out. They are saying because n times p naught and 1 minus p naught, and we have to see, is it greater than or less than 10, because again, for us to be able to do that confidence interval hypothesis testing, we have to kind of check these. So your p naught value is going to be those parents, 281 out of the 900. So 281, 900, and this will be 281 divided by 900. So kind of calculating that point estimate. Now let's go ahead and calculate the, oh, sorry, wrong place. That should go here. X divided by n. And the p naught, sorry about that, is actually that original probability they told us, which was the 49%. So 49% in decimal will be 0.49. So you can see 49% from 20 years ago, and then when I did x divided by n from the recent survey, you're actually getting 0.312222, right? So definitely the numbers have changed. Now let's calculate this n times p naught, 1 minus p naught. So n, of course, is now 900 multiplied by p naught, which is 40.49. Multiply that with, in parentheses, I'll do 1 minus p naught. And you can see that number is definitely greater than 10 because you're getting 224.91. Okay, so we will say this value is equal to, they're asking us to round to 1 decimal place. So that will be 224.9. This is, of course, a number greater than 10. The sample size, again, they're not telling us, but obviously we're going to make the assumption that our sample size will be less than 5% of the population size. We will say that the sample, and they didn't really, again, tell us, if you read the wording of the survey, they're not telling us that this is a random sample or not of those 900 people or parents we're talking to. So we can say it can be reasonably assumed that the requirements, the sample, can be reasonably assumed to be random. The requirements for testing the hypotheses are satisfied. And, especially the big part here was this number has to be larger than 10. So we definitely met that. We can make the assumption about the sample size being less than 5%. Now we're getting into the null and alternative hypotheses. So in this case, the question they're asking us is very generic because they are saying, do the parents feel differently today? So they're not saying, has the probability gone up? Has the probability gone down? So there's no discussion of that. They're just saying, do parents feel differently today? So when you're doing the null hypotheses and alternative hypotheses, remember we are talking about the probability here. And for the original probability, we had 0.49 or 49%, so 0.49 over here. Okay, there we go, 0.49. Now for the null hypotheses, of course, we'll go down to P again, but they're saying fields differently, right? So that actually means you are using not equal to, not less than or greater than. And of course, we want to know, has it changed from 0.49%? So that's going to be our null and alternative hypotheses. Now they're asking us to determine the test statistics Z sub 0 over here. And this is where you have this formula. And again, I've just copied the formula over from your textbook. So equal to, on the numerator, I'm going to put this in parentheses for my numerator part. We are doing P hat minus P0. Oh, there we go. And then you're dividing this by the square root of P naught. So again, 0.49 in multiply that by parentheses 1 minus P naught. And then we're dividing it by N, which will be 900. Close your parentheses for the square root. So you can see I put the numerator P hat minus P0 in parentheses so that Excel or Google will know the subtraction has to happen first, and then you divide by the square root of that denominator over there. So you can see our test statistic is coming out to be negative 10.669, rounded to 2 decimal places. So negative 10.669 will of course become 67. So you've got your test statistic, and now they're asking us to determine our critical values, and that will obviously come from our table over here. And actually for the critical values, we will have to use the alpha value they gave us over here. For the level of significance, they said use the alpha value of 0.05. So we actually need to do that first. So this one here. Okay, looks like, I don't know why I have that typed in, because obviously that changes with each problem. So this is actually will need to be changed because I think I left it at a different level of significance. So for now, our alpha is 0.05. So of course, alpha divided by 2 will then be 0.025. So that's what we're going to need. 0.025. So we should be back in this part of the table. And you will see over here when we talk about 0.025, we're back over here. And if you remember, we had that same thing in our section 9.1 problem. And this will actually correspond to 0.06 for this column over here where you have the 0.205. Okay, so that's how we're using this table over here. So you will actually do plus or minus 1.96. So a little bit different than what we had done before, because we had ignored the negative sign last time, but here we will keep both the positive and the negative. And then over here, I'm kind of talking about how you need to compare your critical values with the test statistics. So the idea is if your Z sub 0, which is the test statistic value over here, is less than the negative side of the critical value, the negative 1.96, or if your test statistic is greater than the positive side of this critical value. Based on that, you will reject the null hypothesis, otherwise you don't reject it. So in this case, you will see that your negative 10.669 and negative 1.96. Well, is negative 10.669 less than the negative 1.96? Yes, it is. Yeah. So we are actually satisfying this condition over here. Obviously we cannot do a comparison with the Z being greater than the positive 1.96. So in this case, since we satisfy this, you will actually reject the null hypotheses in this case. So let's go ahead and clear this out. This came out to be 1.96. And remember, you do go with the positive negative option on this. And since we recognize that we will need to reject our null hypotheses, now it comes down to, which option you are choosing. Is it going to be option B? Is it going to be option D? We are saying in option B, there is sufficient evidence to conclude that the number of parents who feel that the students are not being taught enough math and science in 20 years is significantly different. The D part says reject the null hypotheses, but they're saying there is insufficient evidence to conclude that the number of parents who feel students are not being taught enough math and science is significantly different in the 20 years. So it's really the difference of, do you think there is sufficient evidence or is there insufficient evidence? So what do you guys think? Option B or option D?
B, there is sufficient evidence.
There is sufficient evidence. Yeah, and look at that numbers right over here with your P naught and the P hat. I mean, that is a significant difference, right? From 49%, you're basically at 31%. So we can say, yes, there is sufficient evidence that parents are feeling differently from 20 years ago to now. So that's kind of how, these hypothesis tests are basically used to determine, okay, we've done the survey, we've got the results, but now let's try and make sense of it and see, hey, are we able to use this a little bit more? So this test that we did over here, and the reason why you have the positive and negative 1.96 actually comes from this symbol over here, because this is what we call as we did a two-tailed hypotheses testing. So even in, and I don't know if I mentioned that in this handout. Yeah, so you can see over here, I do talk about how this is a two-tailed test that we are doing. Now, if you were only going to use the less than or greater than, in that case, you would have a right tail or a left tail test in that. So remember, that just depends on, your hypothesis testing and what kind of symbol you are using. So, again, practice a little bit with those. And then if you guys have any questions, anything you want to ask in any of these two homework assignments, just shoot me an email. Because like I said, this is a little bit of a different kind of statistics that you may not have seen like in a basic stats class if they don't go into so much detail. So that's why, these are some of the examples I like to go over with you. So please don't hesitate to reach out. If I can help you with anything, send me an email. And just to remind you, if you have not sent an email for your password for the exam, please go ahead and do that right away. Okay, guys, if you want to stay back and ask a question, you can. Otherwise, I will see you next week. So be careful, guys. Stay safe. And I'll see you next Wednesday. Bye. Take care. Hey, Sky, did you have a question?
Did you get the email I sent for the password for this next for the next exam? Because I sent it kind of late at night, so I didn't know if you saw it or not.
I think I did. Yeah, I remember seeing your email, and I can go back and check to make sure that I have that. Yes, I do see your emails, guys. So yeah, as soon as I'm done with class, I'll go ahead and start sending those out.
Okay, thank you.
Thank you. Take care.
Have a great rest of your day.
You too. Hey, Cody.